Hi, welcome to the video on the calorimetry problems. This is a video to replace the video that was previously linked in the document that is no longer available. So I will make my own video going over the problems. This is from part 1, the simple problems. These are example problems for 3 and 4. So let's start with example problem 3. It says how much heat is, and there's a correction there. It should say released released when lowering the temperature of 500 grams of water from 20 degrees Celsius to 10 degrees Celsius. And the reason why there's that correction is because if you're going from 20 degrees to 10 degrees Celsius, you're cooling down, and so you're releasing heat, not needing or absorbing it. And they give you the specific heat of water. All right, so how much heat is released to lower the temperature of 500 grams of water from 20 degrees to 10 degrees Celsius. So the equation that we always use is Q equals MC delta T. Q, the symbol is the symbol for heat, so that's what we're looking for. That's my question mark because it's saying how much heat. They give me the mass of the water, 500 grams. They give me the specific heat or heat capacity of the water, 4.184 joules per degree Celsius. And they give me the change in temperature. Well, they didn't give me the change in temperature directly, but they gave me the initial temperature, TI, which is 20 degrees, and the final temperature, which is TF. So with that being said, I can calculate my change in temperature. Delta means change. TF minus TI, final minus initial. And that's 10 minus 20, which gives me negative 10. And the sign is super important here because when you're doing these problems, the sign indicates whether you gain or lose. So if you're gaining heat, your Q would be positive. If you're losing, it's going to be negative. All right, so I go ahead and I plug this into the equation. Q equals MC delta T. So my Q, which is what I'm solving for, is equal to 500 times 4.184 times negative 10. And that's 10.0, by the way, because I'm using sig figs here. So when I multiply this together, I'm going to get negative 20,920 joules. What I need to do now is I'm going to round this according to sig figs. By the way, on the assessment, if you don't round to sig figs, that's fine. But I'm going to show you how I round to sig figs anyway. So just to keep track of how many sig figs I have, there's a decimal here at the 500. So all of these zeros count. So this is 3 sig figs. This one has 4 sig figs. And here we have 3 sig figs. Because that's 10.0. And the reason why it's 10.0 is because when you're subtracting or adding numbers, according to sig fig rules, you use the least number of decimal places. I had 1 decimal place here, 1 decimal place here. When I subtracted it, instead of writing negative 10, I had to write negative 10.0. And so this has 3 sig figs, I'm sorry. 1 decimal place, 3 sig figs. So when multiplying, we're going to use the least number of sig figs. So that means that the least number of sig figs would be 3, right? Because you have 3, 4, and 3. So 3 is the smallest number there. So I'm going to cut this off between the 9 and the 2. And so I'm going to get my Q to be negative 2.09. And then I'm going to use the rest as placeholders. So I'll use zeros as placeholders here. So Q is equal to 20,900 joules. All right, the next problem is number 4. If 200 joules of heat is added to 25 grams of iron at temperature at 15 degrees Celsius, what will be the final temperature? And they give me the heat capacity of specific heat capacity of iron. So again, the equation is Q equals MC delta T. Q is 200 joules, M is 25 grams. C is 0.45, delta T is final minus initial. Now my initial temperature is 15 degrees. How do I know that's my initial temperature? Well, if you read the problem, it says if 200 joules of heat is added to 25 grams of iron at 15 degrees Celsius. That means we're starting there. That's my TI, my initial temperature. And I'm asked to find the final temperature, so that's clearly my unknown. So in the case where you're asked to find either the final or the initial temperature, what you're going to do first is you're going to use the Q equals MC delta T equation to solve for delta T. Once you solve for delta T, then you can go ahead and find the initial final temperature by plugging it into this equation. Delta T equals TF final minus T initial. All right, so I go ahead and I plug in, I'm going to solve for my delta T first. So I plug in my Q, which is 200, my mass, which is 25, my C, which is 0.45, and my delta T is my unknown. And the first thing I do is I multiply the numbers that are on the same side as my delta T. So 25 plus times 0.45 gives me 11.25. I'm just simplifying the right side. Then to finish solving for my delta T to isolate it, I'm going to divide both sides by 11.25. That cancels that out. And I get delta T is equal to 17.8. I'm using the 3 sig figs here, even though technically it would be 2. But this is not my final answer, so if you want to go up an extra sig fig when it's not your final answer, that's fine. So a little side note there. But at any rate, I have my delta T to be 17.8 degrees Celsius. And then what I do is I plug that delta T into my equation. Over here, the delta T equals final minus initial temperature. So 17.8 is equal to TF, which is what I'm looking for, minus 15. And so I'm going to add 15 to both sides. And this gives me, when I do that, I get a TF of final temperature of 17.8 plus 15. And that's 32.8 degrees Celsius, 32.8 degrees Celsius. Now, with that being said, because 15 degrees has no decimal places, and I'm adding or subtracting here, right? When you're doing that, we're going to use the least number of decimal places. That means my cutoff has to be between for sig figs, has to be between the 2 and the 8. And because the number to the right of the cutoff is greater than 4, so 5 or above, I'm going to have to round that up to 33 degrees Celsius. So my final temperature, the final temperature of the iron is going to be 30 degrees Celsius. So if you take a piece of iron and add 200 joules of heat to it, the final temperature, if it started at 15 degrees Celsius, would be 33 degrees Celsius. All right, so that's part 1. There's one more problem we're going to look at, and that is example problem 1 from part 2. And again, this is to make up for the fact that the video that was linked is no longer available. Okay, so in these problems, you're taking a hot piece of metal and you're putting it into cool water. Could, of course, be the opposite, a cool piece of metal putting into hot water, but not as spectacular when you do it that way. So you have a hot piece of metal and you're putting it into cool water. And what happens is the metal will lose heat energy and the water will gain heat energy. And you can use the fact that the heat lost by the metal is equal to the heat gained by the water, equal in magnitude but opposite in sign. So Q of metal, heat of metal, is equal to negative Q of water. Equal magnitude, opposite sign. So with that being said, in this problem, where it says a hot piece of iron with a mass of 75 grams and a temperature of 200 degrees Celsius dropped into 250 grams of cool water at a temperature of 18 degrees Celsius, and they want to know what's the final temperature of the water and the iron, and they give us a specific heat, we can use these two equations and the variables for each the metal and the water to solve for the final temperature. So the best thing that I like to do, or not the best thing I like to do, what I find helpful is I find it helpful when I make a list of all the values for my metal and all the values for my water. So starting with the metal, I just write the equation Q equals MC delta T on top. You don't have to, but it's helpful for me to keep track. And not all of the values I'm going to actually fill in, but I just relist them. Q, M, C, delta T, and then I also break delta T down into TI and TF because a lot of times that's helpful. A lot of times they don't give me the change in temperature. They'll give me the TI or the TF or ask me to find those values, so I like to list them. Same thing on the water side. Q, M, C, delta T, and then I just fill it in. So the Q of the metal is not given. That's the piece of information I actually don't need in this problem. The mass they gave me is 75 grams. The C, specific heat, at the bottom here is 0.45 joules per gram degree Celsius. The delta T I don't have, but I do have the initial temperature of the iron is 200 degrees Celsius. And I'm looking for the final temperature of the iron. Going on to the water side, the Q of the water, again, I don't have that and I don't actually need it. The mass of the water is 250 grams, right? And the C, or specific heat capacity of the water, is 4.184 joules per gram degree Celsius. My delta T I don't have, but they gave me the initial temperature of the water, and it's 18 degrees Celsius, and I'm looking for the TF. So looking at this, I have 2 question marks here, the final temperature of the metal and the final temperature of the water. Now, maybe you're thinking that these are different values, but they're actually going to be the same value. The initial temperature of the metal and the water are not the same, but the final temperature will always be the same. I'll say that again. The final temperature for the metal and the water will always be the same. And that's because when you have something that's hot in contact with something that's cool, the hot thing is going to cool down, so its temperature is going to decrease, and the cool thing is going to heat up until their temperatures are the same. And that's called thermal equilibrium. So this concept that as long as their temperatures are different, they're going to exchange heat until their temperatures are the same. And so the final temperature, when they'll stop changing their temperatures, is when the temperatures are the same. So with that being said, we actually only have one unknown, which is the TF for both the metal and the water is going to be the same value. Now that I have that all set up, I know all my values, what I do is I'm going to plug them into the MC delta T equation. But here's the thing. I can't go ahead and put in delta T for the metal and the water. 1, because I don't know the final temperature. But 2, the change in temperature of the metal and the water are not the same because they have different specific heat capacities. So even though they exchange the same amount of heat, how much their temperature changes will depend on their specific heat capacity. So the delta T's here are actually not the same variable, or not the same unknown. But the TF is. So what I can do is I can replace delta T on the metal and the water side with TF minus TI, the final temperature minus initial temperature for the metal, and the final temperature minus initial temperature for the water. And that's what I've done here. Once I have that, I can go ahead now and just plug in everything. So my mass goes in first for my metal, 75, specific heat is 0.45, and then that's going to be multiplied by TF, which is what I'm looking for, minus the initial temperature of the metal, which is 200. On the water side, I do the same thing. The mass of the water is 250 grams. The specific heat is 4.184. And I'm going to multiply that by the final temperature of the water minus the, I should just say final temperature of the system because it's the same as the metal, minus the initial temperature of the water, which is 18 degrees. So remember, these 2 TFs, even though they're in different colors, they're the same value. Okay, so how do we solve something like this? The best thing to do is try and simplify it as much as you can first. So on both sides, I multiply out the 2 coefficients in the front, so 75 times 0.45 gives me 33.75. And on the metal side, negative 1, because don't forget that negative out there, times 250 times 4.184 gives me negative 10.46 on the water side. And then what I do is I'll distribute next. So on both sides, I'm going to distribute the coefficient in front of the binomial TF minus TI, right? So I distribute the 33.75 times TF and 33.75 times negative 200. And that gives me this, 33.75 TF minus 6750. On the water side, I distribute the negative 1046 to the TF minus 18, and then that gives me negative 1046 TF plus, because the negative times a negative is positive, plus 18,828. All right, so now to solve this, what I want to do now is combine like terms. And I like to avoid negatives. So whatever is negative, I typically move it to the other side using inverse operations. And when I say negative, this negative represents a minus sign because you have 2 terms. They're not multiplying, they're subtracting in this case. So I'm going to add 6750 to both sides. It cancels it out on that side. And what I get here is I just add those 2 together, and I get 25578. I go ahead and I bring down everything else. So there's a plus sign in between them. And this is canceled out, so that's gone. And I get 33.75 TF on the left side. Okay. So now I want to continue to combine like terms here. So in this case, I'm going to move the 1046 TF over. So 33.75 plus 1046 TF, and then that gives me, oops, put that wrong there, plus 1046. All right, I get 1079.75 times TF is equal to 25578. All right, because the 1046 TF cancels out there. Okay, so now the last thing I should do is divide both sides by the coefficient in front of TF. And I get the TF to equal 2369 degrees Celsius. Okay, so now the last thing I would want to do is to figure out my significant figures. In this case, if you go back up to your work here, you see that the least amount of significant figures in the multiplication process was 2, so that means this is going to end with 2 sig figs. So I'm going to go ahead and cut it off between the 3 and the 6. So my final temperature becomes 24 degrees. Of course, I'm going to round up degrees Celsius. Okay. So that is the work here for these problems. Hope you found this video helpful. Have a quality day.